Okay, this video is called Introduction to Linear Programming. Now, linear programming, or LP, is a problem-solving procedure for finding the minimum or maximum value of a function subject to certain conditions placed on the variables. Now, the variables in a linear programming type problem are specifically called decision variables. And the function is called an objective function. Or it's sometimes called a profit function. Because often in maximization type problems with linear programming, you're looking to maximize a profit for a particular type of business. Now, the conditions that are placed on the decision variables are called constraints. And the constraints are expressed as a system of inequalities. Now, the graph of the constraints, that is the graph of this system of inequalities, produces something that's called a feasible region. And the maximum and minimum values of the objective function occur at the corner points of the feasible region. And one of these corner points is going to provide what we call the optimal solution. Now, let's take a look at what this a linear programming example here, and some of these terms are going to start to make a little bit more sense. So this example has to do with the Lego Furniture Factory, and we looked at this example a little bit already in class. Lego Furniture Factory produces only tables and chairs. A table is made of 2 small pieces and 2 big pieces, while a chair is made of 2 small pieces and 1 big piece. And the number of pieces available is limited by the supplier to 6 big pieces and 8 small pieces per day. Lego Furniture Factory makes a profit of $16 for each table sold and $10 for each chair sold. How can the production manager maximize the amount of profit given the limited resources available for production? Okay, so first thing we want to do is we want to define what we're going to call our decision variables. And we're going to have 2 decision variables in this example. Our first decision variable is going to be the number of tables produced per day. And our second decision variable is going to be the number of chairs produced per day. Now, notice I'm naming my decision variables not x and y, but x1 and x2. It's going to be my x1 axis, and this is going to be my x2 axis. And I'm doing that because this is a relatively simple example that we're starting out with. We're going to be getting to some more complicated examples where we have more than just 2 decision variables, and it just makes it easier to number them, starting with number 1 and then number 2 as we go. Now, the objective function for this particular example, our objective function is going to be, in this case, we actually are going to call it a profit function because we're trying to maximize the amount of profit we're going to make selling our tables and chairs. Well, our profit function, our profit is going to depend on how many tables and chairs we sell. And we're told that Lego Furniture Factory makes a profit of $16 for each table sold. So our profit is going to be 16 times the number of tables that we sell, plus, let's see, we make $10 for each chair sold. So we're going to have, our profit is going to also include 10 times the number of chairs sold. So this is going to be our total profit. 16 times the number of tables plus 10 times the number of chairs. Okay, now we've got our decision variables and our objective functions. Our objective function. Now we want to talk about constraints. Now for this problem, it turns out we're going to have a total of 4 constraints. Our first constraint, notice it says in the problem that the number of pieces available to construct our tables and chairs is limited by the supplier to 6 big pieces and 8 small pieces per day. So we've got a constraint on our big pieces. Let's call that our big pieces constraint. And we're going to have a constraint on our small pieces. We'll call that our small pieces constraint. And we're going to talk about these other 2 constraints in just a minute. So our big pieces constraint. We are limited to the number of big pieces. We only have 6 big pieces per day. So basically our big pieces constraint is that the number of big pieces we have is going to be, or the number of big pieces that we can use to make tables and chairs is going to be less than or equal to 6. In other words, we can make as many tables and chairs as we want as long as we use less than or equal to 6 big pieces. Well, how am I going to express this as an inequality? Well, the number of big pieces that I use, it's going to be less than or equal to 6. The number of big pieces that I use, it's going to depend on how many tables and how many chairs I make. Specifically, I'm told a table is made of 2 small pieces and 2 big pieces. Well, if a table uses 2 big pieces for each table that it makes, then the number of tables produced per day is x1. Then 2 times x1 is going to be the number of big pieces that I use in making a table. I'm also told that a chair is made of 2 small pieces and 1 big piece. That means that for every chair I make, x2, I'm going to be using 1 big piece. So the total number of big pieces that I'm going to use is going to be 2 times however many tables I make, plus 1 times however many chairs I make. And this total number of big pieces has to be less than or equal to 6. So this is my first constraint. This is my big pieces constraint. I also need to come up with a small pieces constraint. And my small pieces constraint is just going to be the number of small pieces. And I'm told that I'm limited in the number of small pieces by my supplier. I can only use 8. I can use up to 8 small pieces per day. So my number of small pieces is going to have to be less than or equal to 8. Well, how many small pieces am I going to use? That depends on how many tables and chairs I'm going to make. So let's see. A table is made of 2 small pieces, so I use 2 small pieces in each table I make. So 2 times the number of tables I make, plus, let's see, a chair is made of also 2 small pieces. So 2 times the number of chairs I make. This is the total number of small pieces I'm going to use, so that has to be less than or equal to 8. So here's my small pieces constraint expressed as an inequality. Now, at first glance, it looks like, well, those are the only 2 constraints, the number of big pieces and small pieces provided by my supplier, but it turns out there are also a couple of other constraints that we use very often in these types of problems, and these constraints are what we call the non-negativity constraints. And the non-negativity constraints are just there to remind us that we can't make fewer than 0 tables and chairs. In other words, we're going to have a constraint here that says x1, the number of tables produced per day, has to be greater than or equal to 0. We could make 0 tables, but we can't make a negative number of tables. And we're also going to have a constraint for the number of chairs. The number of chairs that we make has to also be greater than or equal to 0. We can't make a negative number of chairs. So these are called our non-negativity constraints. So we have a total of 4 constraints. And now that we've expressed these constraints as inequalities, we want to graph them on our set of axes here. So let's graph these inequalities. So here's my big pieces constraint. I want to graph this inequality. And the way I'm going to do it is I'm going to use the method where I essentially graph my 2 what I used to call my x-intercept and my y-intercept. This will be my x1 intercept and my x2 intercept. So if I let x1 be equal to 0, so let x1 be equal to 0, then x2 is going to be 6. So 1, 2, 3, 4, 5, 6. And if I let x2 be 0, then 2 times x1 is equal to 6. That's going to mean x1 is going to be equal to 3. So 1, 2, 3. So here are my x1 and x2 intercepts. And if I connect these up with a line, then here is a graph of my big pieces constraint. So there's the graph of my big pieces constraint. Okay, my small pieces constraint, I'm going to do the same thing. If I let x1 be equal to 0, then this term goes away, and I've got 2 times x2 is 8, so x2 would be 4. So 1, 2, 3, 4. And if I let x2 be equal to 0, then this term goes away, and I have x1 is going to be equal to 4. So 1, 2, 3, 4. So there are my 2 intercept points for this constraint. And again, if I connect these up, then here I have a graph of my small pieces constraint. Now my other 2 constraints are my non-negativity constraints, which just says that x1 has to be greater than 0 and x2 has to be greater than 0. So those are going to give me the other 2 boundaries of what's going to be my feasible region. So in other words, my feasible region is going to be all of the places on my graph that are less than my big pieces constraint, less than my small pieces constraint, and greater than my non-negativity constraint. So that's going to be this region right here. So this region is going to be what we call our feasible region. Now that I have graphed my constraints and identified my feasible region, I want to next identify the corner points, because I know that it's going to be at one of these corner points that I find the optimal solution or the maximum profit that I can get. So my corner points, I've got essentially a kind of a quadrilateral here. There's a corner point, there's a corner point, there's a corner point, and there's a corner point. So each one of these corner points, the coordinates for each one of these corner points, this one is 0, 0. This corner point is 0, 4. This corner point, what we would do normally is we would graph these equations in our graphing calculator and find their intersection point. This one, it turns out, and it looks pretty close on this graph, the intersection point here is at 2, 2. And if you graph these 2 inequalities or these 2 equations on your graphing calculator, you'll see that that's the intersection point. And then my other intersection point is here at 3, 0. So now I've identified my 4 corner points. Now I want to calculate what is the profit that I would make at each one of these corner points. In other words, for each one of these corner points, how much profit would I generate? Well, let's try them out and see. Write down my 4 corner points. 3, 0. And let's just calculate the profit for each one of these corner points, or for each one of these combinations of tables and chairs produced. Remember, this is x1, it's my first coordinate, x2 is my second coordinate. Okay, so my profit function is 16 times x1 plus 10 times x2. For this one, I would have 16 times 0 plus 10 times 0. Well, that's not very hard. That profit's going to be 0. So it looks like just calculate or just producing 0 tables and 0 chairs, I can see I'm not going to make any profit at all. What if I produce 0 tables and 4 chairs? Well, let's see what profit that produces. 16 times x1, so 16 times 0 plus 10 times x2. So that's going to be 0 plus 40. So that gives me a profit of 40. How much profit do I make if I make 2 tables and 2 chairs? 16 times 2 plus 10 times 2 let's see, that's going to be 32 plus 20, which is 52. So I make more profit if I make 2 tables and 2 chairs than if I make 0 tables and 4 chairs. And let's check this last one. 16 times 3 plus 10 times 0. So that's if I make 3 tables and no chairs. So 3 times 16 is 48. And I can see that my maximum profit is going to occur right here. In other words, my maximum profit of $52 per day occurs when I make 2 tables and 2 chairs.